In this video, I'll be going over inverse functions. Before we start, before we start talking about inverse functions, we need to define what a one-to-one function is. Now, a one-to-one function is where each output comes from only one input. And to determine whether a function is one-to-one, we use the horizontal line test. That works on a graph of a function. So looking at these three mapping images, what we can see is that in this first one here, each of the y values or the output values is getting pointed to by only one arrow. So that tells us that this is one-to-one. In our second one here, what we notice is that this output, y2, is getting pointed at or getting pointed to by two separate x values. So while this is a function, is a function, but not one-to-one. Okay, so I think you might have heard this example before, but let's say we're talking about a function where the inputs are people in a room and the outputs are what all of those people's birthdays are. In this first image, all the people, which are represented by these x values, each person has a different birthday. So each arrow points to one and only one, or each birthday is getting pointed to by only one person, by only one x value. In the second image, though, this would be like person x2 and x3 both having the same birthday. So, for example, two people have the birthday of October 14th. Now, this still represents a function, but it's not a one-to-one function. And then in this third image, this point, x2, or this input, is pointing to two separate outputs. Not only is this not one-to-one, that doesn't even apply because this is not a function. And back to the birthday example, this would be like one person having two separate birthdays, which doesn't make sense. Okay, so that's an overview of what it means for a function to be one-to-one. Looking at these three graphs, using the horizontal line test, what that tells us is if we can draw a horizontal line through the graph and it hits at least two places or more, then that is not one-to-one. So this is not one-to-one, although it's still a function because it passes the vertical line test. This second graph, g of x, is one-to-one because no matter where I draw a horizontal line, it's only going to hit that graph in one position. And then this absolute value graph is not one-to-one because we can see that I can cross that graph in two separate positions. And thinking about this a little bit more deeply, what this is saying is that the input of 3 and the input of -3 both give me a y value of 3. So we would say f of 3 gives 3. I'm assuming this is f of x. Let's just make it explicit. And f of -3 is also 3. So because because two different inputs give the same output, that is why this is not one-to-one. All right, and then let's look at these algebraic examples. So I have three functions, and the quickest way to determine whether a function is one-to-one is by graphing it. 2x plus 5, that's just a line with a slope of 2 through the y-intercept of 5. Any line is a one-to-one function. The second function, x squared minus 1, well, that's a parabola that is shifted down 1 unit. And that is, let's try that again. That is not going to be one-to-one because this does not pass the horizontal line test. So we'd say not one-to-one here. And again, this input and this input both give the same y value as an output. So that's why this is not one-to-one. And then that third graph, if you can remember what that looks like, well, that's just an absolute value function, a square root function. Looks like this. It levels off as we get closer to x equals infinity, but it never truly gets horizontal. So no matter where I draw that line, it's only going to hit the graph in one location. Okay, so why do we care about whether a function is one-to-one? Well, we care if a function is one-to-one because if a function is one-to-one, then we can find its inverse function. So that's what we'll do next here. So let f represent a one-to-one function, then y is in the range of f. Then if y is in the range of f, there is only one value of x in the domain of f, such that f of x equals y. We define the inverse of f, called the inverse function of f, denoted like this, if and only if y equals f of x. So that's a long way of saying that if we have a one-to-one function, we can find its inverse. And we use this notation to indicate that this is the inverse of the original function f of y, or f of x. Yeah, and there's a couple ways we can do this, and actually how I'm usually going to write this. Let's see here. Okay, there we go. F of x is our original function, so f inverse of x would be the inverse function. That's how we'll be writing this. So a lot of words to just say, if we have a one-to-one function, we can find its inverse function. And what's happening is the original function, in the original function, x is the input and y is the output. In an inverse, these reverse, these swap places. So y becomes the input, x is the output. Okay, and graphically what's happening is, let's go up to one of these that is one-to-one. So let's look at this graph right here, and I'm going to erase my lines. Okay, so what's happening is on a on an inverse function, it gets reflected, the graph gets reflected about the line y equals x. Okay, so that graph is going to look something like this. So that's what the inverse of g of x would be, or g inverse of x. That's what that graph would look like. Okay, and I guess the reason why we wouldn't want to, or we can't find the inverse of a function that's not one-to-one is, let's suppose I take this absolute value function graph. If I reflect over that line y equals x, I get this graph, and this is not a function. It does not pass the vertical line test. So that's why we must have a function. We must have a function as one-to-one in order to find an inverse that is also a function. Okay, so let's go down to this, these two examples. Find the inverse function for f of x equals x plus 1 over x minus 1 and verify that it's the inverse of the original function. Okay, so first let's find the inverse. So what we want to do in order to find the inverse, we'll follow these steps. So we'll swap, or I guess we should say replace f of x with y, and then we're going to swap x and y. Okay, and then what we do is solve for y, and then lastly replace y with the inverse notation. Now let's go ahead and find the inverse, but before we do that, let's verify that this is one-to-one. And the best way to do that would be by looking at the graph. I don't know 100% what this graph looks like. We could look on Desmos, but this is going to be some sort of rational function, something that has a parent function that looks like that. Those rational functions are one-to-one. The instance when it would not be one-to-one is if I have a rational function that's something like this, where this does not pass the horizontal line test. But this type of graph looks more like this one, so it is one-to-one. And we could verify that more precisely by looking at the actual graph. But this one's one-to-one, so let's go ahead and follow these steps to find the inverse. So I'm going to replace this f of x with y, and then I'm going to solve for replace the f of x with y, and then I'm going to swap x and y. So this becomes x is equal to y plus 1 over y minus 1. And then I'm going to multiply both sides by y minus 1. So we get x, y minus x on the left-hand side. Y minus 1's cancel. I'm left with y plus 1. Let's collect all the y's on the same side and the x's on the other side. Now on the left-hand side here, I need to factor out a y and then divide by x minus 1. So I get y is equal to 1 plus x over x minus 1. And then swapping out the y with the inverse notation, I get 1 plus x over x minus 1 as the inverse. Okay, now what we want to do is we want to verify that that is actually the inverse. And so to do this, what we must show is that f of the inverse is equal to f inverse of f of x. So what we do is we compose these two functions with themselves in opposite ways, and then if we can show that they're equal, then we know that this is in fact the inverse of the original function. Let's go ahead and do that. So on the left-hand side, I'm going to take the inverse that I found, and I'm going to input it into the original function. So in place of x here, I'm going to input 1 plus x over x minus 1. So 1 plus x over x minus 1 plus 1 divided by 1 plus x over x minus 1 minus 1. And then I'm going to do the reverse on the right-hand side. So I'm going to take the original function, I'm going to input it into this inverse. So I'm going to have 1 plus, in place of x, I'm going to write the original function. And then in the denominator, in place of x, we're going to put x plus 1 over x minus 1 minus 1 like this. So we just have to simplify the left-hand and right-hand side and make sure that those are the same. So on the left-hand side, to add 1 to that fraction, I need to multiply the top and bottom by x minus 1, which is the common denominator. So on the left, we're going to get, I'm just going to write this with the same denominator. We get 1 plus x plus, when I distribute the 1, I just get x minus 1 in the numerator. Oops. Let's keep that as green. And then in the denominator, same idea. I'm going to have a new denominator in that bottom fraction of x minus 1. In the numerator, I get 1 plus x. Now be careful here, I have a negative 1 getting distributed. So negative 1 times x is negative x. Negative 1 times negative 1 is plus 1. All right, so in that fraction, when I have a complex fraction with like denominators, those can cancel. Then what remains is I have a 1 plus x minus 1. So I have 2x in the numerator. In the denominator, these x's are going to cancel, so I have over 2. And the 2's cancel, so I just get an x on the left-hand side. Now let's see if we can simplify the right-hand side down to also be just x. X minus 1 is what I need to multiply these 1's by to get a common denominator. So we get x minus 1 when I do 1 times the numerator, x minus 1, plus x plus 1, and my new denominator, my new common denominator is x minus 1. And then downstairs, again, my common denominator will be x minus 1. I have this x plus 1 right here, and then minus 1 gets distributed. It's minus x plus 1. So things are going to operate in much the same way as on the left-hand side. Those x minus 1's can cancel. Negative 1 and positive 1 cancel, so I have 2x. And then these x's cancel. I'm left with 2 in the denominator. 2's cancel. X equals x, which is what we want. So because the left-hand side is equal to the right-hand side, I've shown that what I found here, I've verified that that actually is the inverse of the original function. All right, now let's do one more of this. We have our function f of x is equal to x over x plus 3. So I'm going to replace the f of x with a y, and then I'll swap that. So I get x is equal to y over y plus 3. Now you might want to pause the video here and see if you can actually solve this equation for y. All right, here's how we're going to do this. Multiply both sides by y plus 3. Distribute the left-hand side. Collect the y terms on the same side. I'm going to bring everything to all the y's to the right. Factor out a y, I get 1 minus x. So 3x over 1 minus x is equal to y, and I'm just going to replace that y with the inverse notation. So I want to show that this is actually the inverse. I want to verify that, again, by showing f inverse of f of x is equal to f of f inverse of x. Okay, so the input to the inverse function is the original function, so I'm going to say 3 times the original function divided by 1 minus, and then in place of this x, I'm going to do x over x plus 3. And I want to show that that is equal to, now I'm going to go the other direction. So I'm going to input the inverse into the original function. The original function has an x in the numerator, so I'm going to put 3x over 1 minus x in the numerator, divided by 3x over 1 minus x plus 3. So I need to show that these are equal to each other. So we'll work on the left-hand side again. I'm going to distribute that 3. So this is 3x over x plus 3. Down here, I need a common denominator, so I'm going to multiply the top and bottom by x plus 3. And doing so, distributing that 1, I get x plus 3 minus x divided by x plus 3. Again, denominators are going to cancel. And then these x's, x and negative x, also cancel. So I'm left with 3x over 3, which simplifies to just x. And what you may start to notice when you do these is that you're always going to get x equals x at the end if you do it correctly. On the right-hand side, I need a 1 minus x, so I can get a common denominator downstairs. Can't do anything to the numerator, but the denominator, I'm going to distribute this 3. So I get 3x plus 3 minus 3x. Those 3x's are going to cancel. And then these 1 minus x's are also going to cancel. So what we're left with is 3x over 3, which comes out to x. So we have verified that these are equal to each other.